Thank you very much. Well, thank you all for coming out on what's turned out to be not that great an evening. It's all wet and miserable outside. I happen to be in Edinburgh actually because my mother is in hospital here, so I'm actually doing a lot of hospital visiting, and I bumped into somebody in the street, so this kind of happened. I do a reasonable number of talks for the BCS and other organisations, and this is a topic that's become really quite important, and I think is becoming more so as systems are becoming more complex. So the intention is to try and cover some of the principles behind the performance of systems, how they work, and how you might want to think about it from a designer's point of view or a troubleshooter's point of view. My background is, I've been doing sort of big mission critical stuff for a long time. I used to help run a software house as chief designer for about 10 years. The main thing we did was ground control centres for flying spacecraft, communication satellites. And then I left that about 20 odd years ago, and since then have basically worked as a freelance consulting engineer, getting involved in some interesting, difficult, complicated and sometimes fun projects. And so it's kind of a collection of learning and things people I've learned from, things I've discovered, stuff like that. And it's trying to help other people understand a bit more about how systems really behave in the real world. So I'd like to start off with a bit of an intro, then we'll talk about some of the concepts behind performance, and then we'll talk about how system platforms and infrastructure behave. We'll look at then sort of software and coding stuff. We'll look at some designing and testing and some troubleshooting. So it's kind of a bit of a guided tour of the whole thing. One of my problems with the computer industry at the moment is the way that, especially in large corporations, everything has become very, very, very sort of siloed. So you've got, I'm working on something at the moment with data centers in North America. We've got the systems team, we have the programming team, we have the front-end programming team, we have the web server programming team, we have the storage team, we have the network infrastructure team, we have the firewall team, and they don't talk to each other very much. And so one group can happily create a bunch of problems for another group. And something weird and wonderful, oh, and you've got the virtualization team, and something will happen, stops behaving very well, and you've then got this mad scramble to try and get information to find out what's actually going on. And so I'm trying to get people to think more about the whole thing rather than the individual pieces. So what do we mean by a system? Well, that's worth considering, isn't it? So to me, a system is the whole thing. It's not just the bit that we're looking at today, or it's not just this particular thing. You have to, particularly if you're looking for problems and trying to problem solve, look way beyond the boundaries of where you are now and consider the whole thing in its environment. And performance is only a part of it. So there's a whole lot of things going on here. Security is another part. And all of this ultimately is leading up to availability. One of the things that I find is that a lot of organizations really worry about performance of systems. I think the reason they do so is that their experience is that if something doesn't perform, the system is effectively compromised. It's not running properly. It's not available to handle the workload. So their underlying issue is actually availability. Performance is affecting the ability of the systems to do what they're there to do. And so understanding that you're coming at performance is part of availability. Security, if a system is compromised, is part of availability. Understanding how these things are interrelated is actually, I think, quite important. So systems engineering is a term that got coined by NASA a while back. I kind of like this description of it. It's this sort of holistic, you need to look at the whole thing point of view. It works for me. My background is actually mechanical engineering originally. I got involved in ending up designing control systems for power stations and nuclear reactors, stuff like that. But the whole system engineering approach, looking at stuff, is very different to how a lot of the computer industry is currently working, and I actually think it's really, really useful. So, what constitutes something? So this is a diagram of, it doesn't particularly matter what it is. Yeah, it's a large, complex system. You've got machines out here in the middle, you've got the storage layer down the bottom, you've got some kind of internal network and an access network, you've got remote people out in the field, you've got possibly some front-end servers, maybe some big Linux farm running Apache, something like that. All sorts of different pieces that combine to make the whole thing. And there might be, if it's a banking system, what you'll often find is there's a core back-end system, bits of data periodically get moved out to something else, the CRM bit or whatever, and lots of things. And one of the issues there is the speed with which data is propagated and the consistency with which data is propagated and maintaining data integrity so that you have a consistent view of the whole thing. So this is this availability, performance and security stuff. Really, what we're trying to look at here is that a system goes out of, it stops working. It becomes unavailable. It's no longer doing what it's does, or it's behaving in an unpredictable manner. Something bad is happening intermittently. And this is the awful thing about most performance problems. They tend to be transient, intermittent, something strange happens, goes away, comes back. And I don't know, a recent example I got involved in, it turned out that they were running a operating system on an emulator, which was then on top of in a virtual machine, that was on top of a hypervisor, that was then dealing with iSCSI storage. There was a lot of contention because people have been putting more and more virtual machines in. And the straw that finally broke it was a security team introducing more firewall rules and affecting the latency with which data was arriving. And eventually the whole thing started to go wrong in various interesting and complicated ways. And it turned out to be one of those horrible situations where there was no one thing you could fix that would fix it. You actually had to fix this bit and this bit and this bit and this bit in order to then restore correct behavior to the overall system. But it was this succession of failures and inconveniences and things not working properly that eventually took the whole thing down. You've also, of course, got to have systems that have adequate capacity in the first place. It's the ability to scale up and sometimes scale down over time. And you see this time and time again with a lot of systems. Can they handle the peaks in workload? So what does success look like? Well, what's the purpose? What's it there for? And this is delving into the sort of territory of risk analysis. And this is where with projects you're looking at things. Most projects, for example, will handle things of medium risk pretty well. They'll handle things of low risk, usually slightly over catering for it. Where it gets interesting is the really big extreme end of the world. So things that have got a very low probability of occurrence, but truly horrendous consequences if they go wrong. If you want an example from the physical world, the Japanese Fukushima Daiichi power plant that got taken out by the tsunami. It's an incredibly low probability of occurrence, but an utterly hideous set of consequences. And those kinds of risk-making decisions are usually cost-based, because the cost of trying to deal with it is so high that a lot of people look at it and go, yeah, well, the probability of happening is really, really, really low. Yeah, it'll be all right. And then one day, it's not. And how can you demonstrate that you've met the criteria you set? And that's a large part of testing before something goes into service. One of the things I keep coming across quite a lot is people will do what I call functional testing, but they won't do proper scale and scale and load testing. So the first time you find out for real is when the thing goes into production after what appears to have been successful testing. There's quite a nice quote from somewhere. I wish it was mine and it's not, but I'll happily use it. Everybody has a test environment. Some people are lucky enough to have a separate environment for production, right? Which captures it really nicely, doesn't it? That's kind of the heart of the problem. Don't find out in public. Find out privately first. It's much, much, much better. So this bit is about what I'm going to describe as principles of performance. So like most things, there are an underlying set of rules that I think help you think about how systems behave in certain ways. So I'm kind of the opinion now that I can reduce most performance discussions to 3 underlying principles, or 3 underlying things. So bandwidth is all about how much stuff can we get through a system in a given unit of time. So if this was plumbing, it's the size of the pipe. It's how much fluid can I get through a pipe. Yeah. So bandwidth is pretty straightforward, except there's a twist to it. If you take, say, the M8 coming into Edinburgh, what are we measuring? Well, the city bypass. Much lower numbers clearly on the city bypass because it's mostly difficult to get around it. But what are we measuring? Are we measuring vehicles per hour? Are we measuring people per hour? Or are we measuring tons of goods moved per hour? And the answer is, well, it depends on the time of day or what we're interested in today. So what you're measuring will be different depending upon the kind of system it is and the things you're interested in at the moment. So it's not just as simple as how much stuff can I get through. You actually have to think a bit more about the workloads and what's involved and what's the right thing to be looking at. Because you might get different answers depending on what you're looking at. So you might actually want to look at more than one thing to make a decent assessment of what the bandwidth actually is. Next thing is latency. So latency is the delays in a system. And latency is actually really, really important. It's probably more important than bandwidth. It's related to it because clearly the bigger the pipe, the more you can get through. If the pipe isn't full, actually you can get the latency down. But there are some interesting twists and turns to latency as well. So when the thing gets overloaded, there's a mathematical thing called queuing theory, which is kind of useful under these circumstances. And you can start to see variation, quite big variation in the latency and the response times. Talk about that in a moment. The latency of the system, though, determines how much data is in flight through the system at any given instant in time. So if the latency is very big, there's actually quite a lot of data in transit through the system. Yep. If the latency is very small, there's not very much data in transit through the system at any given instant in time. This is where it ties in with availability. If the system were to fail at that point in time, that data will be lost. And this is why databases have things like two-phase commit protocols. It's to handle the fact that you've just lost a chunk of data. So you now have an incomplete transaction, so you now have to back out the wreckage and go back to having consistent data. So latency governs the amount of data that's in flight through a system at any given instant in time. And if you're designing a very high availability system, you might want to factor in the latency aspect of it. Let's say it's an air traffic control system and you're collecting radar returns from an aircraft. Yeah, you clearly don't want loads of that backed up in the system. You want as little in flight through the system as possible. Or if it's a banking transaction system or a stock exchange. Yeah, so you need to think about how much data will be lost. The way that's formalized in availability is recovery. Has anybody heard of recovery point objective, recovery time objective? How much data you're going to drop on the floor when the thing fails? How long it's going to take you back? So that's the tie-in there with availability. So latency isn't just about minimizing the delays. It's about understanding the delays and understanding the consequences of failure and understanding the overall behavior of the system. Latency is also the thing that governs things like peak write I/O rate to disk. If you're writing to a disk in a laptop, normal spinning thing, it's probably got a write latency of around 10, 15 milliseconds. Let's call it 10 because it makes the numbers easy. A 10 millisecond write latency means you can do about 100 write I/O operations a second. If you've got a very big system, very big high performance server with a whole lot of fiber channel storage, and you've got some very nice fancy storage arrays out the back, With a bit of luck, you can get that down to about 0.2 of a millisecond, maybe a bit less. 0.2 of a millisecond translates into about 5,000 IOs a second, which is actually fairly decent. So again, understanding latency and the behavior helps you characterize the system behavior. The third one that's really interesting is mathematically it's diff latency. So it's the variation of latency with respect to time. This is the thing that helps you determine timeouts in software or in network communication layers between systems. So diff latency ideally is 0. But that's going to be pretty expensive to achieve because you're going to need systems that are really quite big for the apparent workload. And so mostly you end up in an argument with people about how much money this is going to cost. But it's these things here will give you some of the tools to explain to them, well, if we size it this big, that's going to cater for average workload. If we size it this big, it's going to give pretty good latency. If we size it this big, we're actually going to get pretty much near 0 variation in latency over time. And for the kind of system we're trying to build, that might be appropriate. For a different kind of system, this might be appropriate. It depends. There's a silly example from the real world of this in action. The city I live in, we have a new concert hall, foyer, and the gents' toilets. The Victorians understood the concept of peak workload. People go to a concert, they turn up, they want to go to the loo, they go to the concert, they go to the interval, have a drink, go to the loo, go back to the concert, right? So the peak demand is this sort of 10-minute window, right, before everybody goes back in the concert hall. So lots and lots and lots of urinals, really easy, turn up, go away. The architects for the new ones put in about 4 per toilet. There's always a queue, right? Because they sized it for average throughput. Oh, look, we've got 2,000 people in the hall, they're here for 3 hours. Not, we've got 2,000 people in the hall, half of whom will need to go to the loo, and we need to get it all done in 10 minutes, which would have given them a very different answer for the size. But the trade-off was space, cost, cleaning costs, a whole bunch of other things, yeah? So there's a design trade-off there, which you could argue they've got wrong. So this whole thing about queues and latency and delays and things backing up is actually really important. So another thing that's happening in the industry is one of the current trends in technology is more and more cores in computers. The assumption is that workloads can be broken down into doing a lot of things at the same time. You could argue that this is somewhat behind some of virtualization as well. People are carving things up into lots of virtual machines, and you're distributing virtual machines into the hypervisor, and you're giving different, virtual machines some work, and inside that it's a single track workload, so you're actually just replicating it several times over. Probably better off to write true multi-core software. So that's a potential problem area. Can we exploit the underlying hardware and the parallelism within it? Something else that happens is multiple I/O paths to storage. Well, that's pretty useful as well because we can potentially distribute, this disk is over that one, path, that path, that path, that path. And we can distribute the I/O load so we can increase the overall total I/O throughput. Multiple paths for network interfaces is the same thing. Now, depending on the protocols, that may or may not give us a problem. TCP/IP v4, for example, doesn't handle multiple paths well because as a protocol it doesn't have an out-of-order packet cache, so it can't reassemble data in the right order. One of the problems with multiple paths for anything is things are no longer guaranteed to happen in the order in which they were done. So if I've got multiple paths in a network and I send data packets down it and it's trying to spread the load across the multiple paths, most of the packets will arrive in the order in which they were sent. But if there's a bit of a delay on any of the one paths, you now start having data arriving in a different order to that in which it was sent. So you need protection mechanisms against that, like packet number tagging, locking, all sorts of good stuff like that. And so bringing in lots of parallelism can create some fun and games. One of my standard sort of troubleshooting things is, I've got involved in people moving some fairly old software off old machines onto newer machines. The old machines were uniprocessor boxes. They put it onto a new machine, and the smallest machine they could buy was a 4-core box. And every so often their software would just blow up. It would just do weird stuff, it would go wrong. And they were and I went, well, you've come off a uniprocessor, you're going onto multiprocessor. What about all the synchronization and the locking and stuff like that? No, we've tested all of that. So, okay, that's really interesting. So I just walked up to the machine and basically stopped 3 of the 4 CPUs and watched their software run perfectly. Started more CPUs and watched their software blow up. Well, thank you, gentlemen. Perhaps you'd like to think about this. You know what their fix was? Leave 3 of the CPUs stop permanently. But it solved the problem, and they'd had enough horsepower in the box to cope with it. So actually, it was a perfectly sensible and valid decision for them to do so. But the implicit assumption now, with a lot of machinery, is that parallelism can be achieved. So rather than going down this, ever faster clock rate thing, we're now going towards slightly lower clock rates, lower power consumption, lower heat generation, more stuff happening in parallel. And if you're really unlucky, Intel tend to ship most of the CPUs with something called hyperthreading on. I'll talk about hyperthreading later. That gives you another illusion. So, how can we exploit this parallelism thing? So most workloads, well, there are kind of 3 categories. Some workloads break down really nicely into lots of things that can be run in parallel with next to no intercommunication. Good example of that. Anybody remember SETI at home? Things like that. It's really easy. Here is a work package. You run it in isolation and you send the results off, and somebody somewhere else joins the results up sometime later. So there's almost no interaction, and it's nice and easy to break up into lots of parallel streams of execution. Some workloads don't break down at all. It's the end of year batch job from hell, doing all the reconciliation stuff in a bank. Yep. There are a few things you can offload, but basically it's a single straight line. Most workloads land somewhere in the middle. So there's a reasonable amount of parallelism to be had, but there's also a lot of communication between the streams of execution and a lot of synchronization, a lot of serialization. Synchronization and serialization are 2 different things, by the way. Synchronization is making sure that only one thing happens at once. Serialization is about making sure that the right things happen in the right order. So they're subtly different, but both important. So handling all these parallel streams of execution and the level of communication is key. So understanding that helps you determine what a suitable design might be for a target system to run that. So it could be that if the level of intercommunication isn't too great and you can get a decent amount of throughput on all the streams, actually a collection of machines that occasionally talk to each other over a network is a pretty good solution. It might be that there's so much intercommunication that the only way you'll deal with it is some monster machine with a lot of CPUs and everything in memory and everything happening at memory speed. Otherwise it becomes infeasible to handle the process. So what's behind all of that is that the advances, I believe, are going to come from improved algorithm design. Anybody read Don Knuth's The Art of Computer Programming? If not, I recommend taking a look at it. There's an awful lot of it. It's a 4-volume thing, and it's really quite chunky. But there's some really nice stuff in it about how things work and how to design and write better code and better algorithms. So it's all this serialization stuff, synchronization stuff, communication. Compilers can do a pretty decent job, but the key thing is this algorithm design stuff. And then something else. Anybody come across what are called state machines? State machines are really useful when you're writing software because they help you determine how wait states work. And so the art of making computer systems go faster is often about not making them go faster. It's about stopping them going slowly. So it's about understanding where all the stall points are, where the synchronization issues are. So understanding this stuff in the context of what you're trying to do will help you write and design better systems, better software. Then the systems scale up. What's going to happen? You know, running out of capacity. And this is where one of the other horrible things about systems. You have the illusion that it's all yours. Actually, often it isn't. You're sharing it with a lot of other people, especially in the virtual world. And so who else are we sharing it with? What's going on? What else can be affecting us? Who else are we affecting by what we're doing? So thinking about things like that. A silly example, and again, something else I saw a while back. Some people wrote some software that ran on a PC that interrogated a database. And they were doing a huge amount of fetching of records, doing some stuff, presenting the results. What they were doing was pulling everything over the network to the local PC, doing the work. Now that was great while 1 or 2 people were doing it. When 500 people started doing it, the network was toast. It just saturated like crazy. A far better design was in fact to send the queries off to the database server, have it do all the work, and just return the results. So it was a relatively simple fix that produced a quantum leap in performance. What made it kind of especially attractive to them to fix the software was that they had already bought the biggest machines they could find. They didn't have anywhere to go. So the old traditional throw more hardware at it solution didn't work. So understanding the implications of how you write stuff is really, really, really key. And how can you increase the overall capacity? Well, the industry's come up with 2 things here, scale up and scale out. Yeah, so more and more and more cores, faster and faster and faster machines, and more and more and more machines. Both of those, it depends on the workload. It depends on this level of intercommunication between all the parallel streams of execution as to how successful things like that are actually going to be. Another topic. Is everybody familiar with the concept of an abstraction layer? Great. Because these are the things that really matter. These are the things that are the illusion. These are the things that create the illusion of you being on your own, that it's all yours. And unfortunately, I'm wandering out of behind you, or behind it, that's not true. So understanding what these are up to and what's going on is key to actually figuring out performance problems. So understanding that what looks to you like it's all yours is not true. You're sharing this with somebody else. Unless you're doing embedded systems and you absolutely know that it's all yours, you're sharing everything with everybody. So, what looks like a disk isn't a disk anymore, right? Because you've got big storage arrays and, hey, here's a piece of storage. It's pretending to be a disk, honest, and actually over there's a massive storage array full of flash storage that's presenting lots of what appear to be disks to lots of different systems at the same time. You're just using bits of them. Networks are the same. You've got things carved up into VLANs. These massive network switches. It looks like it's all yours. It's not. Your little bit here talks to that little bit. There's all these other things going on as well that you don't know about that could be affecting you and the other way around. And so on and so on and so on. Especially in a virtual world. There's just this huge amount of complexity. And this is the thing that's increasing in the modern world in IT. So I call it the hall of mirrors. You have no idea what's really going on and it's all distorted and unpleasant and you don't really like the look of it sometimes. So this hiding stuff makes it really easy to break down the workload, have programmers working on things in isolation, do all sorts of good stuff like that. It also makes it really hard to figure out what's going horribly wrong, especially when it's a transient and difficult performance problem. So that's kind of covered a lot of the principles. Now let's look at some of the bits where they apply. So looking at data network infrastructure, so this is, what's going on here, the access network and the core network. We need to avoid single points of failure because that's where we get availability. So there's some complexity around that. We want to segment out the traffic flows and keep them away from each other. We want to control and manage the traffic flows depending on what they are. So we might be using things like quality of service. We might want to be distributing the loads. There are the bits of trickery called load balancers, companies like Big IP, F5, stuff like that. Cisco, load balancing content switches. Lots of firewalls trying to get in on the act as well. And if people have set firewall rules up and things aren't quite right, you can get all sorts of really strange effects going on. And that makes it really hard to debug the whole thing because you're not quite sure what's going on. And then you've got all the traffic optimization bits. So data networks themselves are actually really quite complex. The end result is quite straightforward. I just want data to go from here to there, thank you very much. But there's all this stuff that's happening in the way. So it's really just a case of being aware of the terminology. So people use VLANs, virtual LANs, to segment a network. Most people do them at layer 2. So this is the MAC address layer. Packets are just tagged. There's an extra tag on an Ethernet frame that tells you which VLAN you're in. The mechanism is called 802.1q. You can also have, where it gets kind of slightly more interesting, this is how hypervisors in virtualization hosts work and some big servers work. You can also set up a server so that it behaves like a switch. So you can actually have multiple virtual network interfaces inside a server sharing the same pair of underlying physical interfaces, and you do the tagging coming out of the server and you do the tagging on, and the switch is set up to accept incoming tagged ports, and that way the traffic out of the servers goes into the right VLANs. Now that sounds quite complex, but if you've got a lot of different data flows and you've split out the data flows to separate them from each other and stop them banging into each other, and you can't buy a server with 32 NICs, then VLAN tagging out of the server can actually be a really good way of splitting up the traffic flows and managing the traffic flows and balancing the load. So it's a really useful design technique. It's also a really useful design technique if you want to bring up different physical servers to do the same job as that server. But that server, when it's running one workload, connects to one set of network stuff. When this one, when it's running, connects to a different set of networks. If everything's VLAN tagged, actually it makes it easier to boot any server to do anything, because all they've got to do is put the right tags on and away you go. The upside is great flexibility. The downside is more complexity, greater need for documentation, and greater need for knowledge within the people who are looking after it and troubleshooting it. So it's a trade-off around from a design point of view. But VLANs can be really, really handy. And most people then map a layer 3 IPv4 subnet onto a layer 2 VLAN and so on and so on and so on. And be aware of things like firewalls and load balancers and bits and pieces. But the key thing is to understand that networks aren't all yours. What happens when a path fails or recovers? How long does it take? How much of a stall is there in the traffic flow? What's the latency during failover, not during normal operation? That then brings around later on into testing. So you have to test stuff not under normal conditions, but under failure conditions. And induce failures to see what really happens on the day. Because lots of people go, yeah, well, it works. And then something happens and it still appears to work, and then something else happens, and suddenly you discover that lots of things that you thought were okay aren't okay. One of my favorites, this happened again last week with some testing. Two network interfaces plugged into two physically separate switches. That's all, should all be in the same VLAN, yada, 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 yada. They'd set the ports up incorrectly on the two switches. We did the failover test, and hey presto, all the traffic ended up disappearing into a different VLAN and all the servers disconnected from each other, which wasn't hugely helpful. It took a little while to figure out what had gone wrong. But once we then realized, we then actually went through a process of actually eyeballing all of the switch configurations and all the port settings, and we caught 2 or 3 others, and we fixed all that, and then thereafter all the failover testing was successful. What happens when paths become saturated? One of the things that network switches will do, and network designers will often do, so you've got servers connected to switches, might be at 1 gig, might be at 10 gig. You've then got pipes between the switches off to the infrastructure, the rest of the infrastructure and the big core switches. If every port on the switch is running at full blast, the big links going up backwards probably aren't big enough anymore. It's a problem called oversubscribing. So if you have oversubscribed switches and the links aren't up to the job, you can trigger saturation if certain things happen within the servers. Statistically, It doesn't happen very often, but it might just happen when you don't need it. And the usual trigger for maximum workload isn't during normal operation. And it isn't particularly when something fails. The usual trigger for maximum workload is recovery from failure, when you've got to start copying all this data around and re-replicate stuff to maintain data integrity. So often you need to test under not just normal operation, but under failure and recovery from failure, which is a lot more subtle. And if you've got all this bandwidth, can you actually use it? Yeah, hell yes, no problem. It's the usual answer. And you can control some of it. And then, there's another fun thing that's recently happened. There's currently a craze for everybody using SSH and end-to-end encryption. Has anybody come across these devices by companies like Riverbed that do WAN optimization? This is another true story. So a company called Riverbed make devices that do WAN optimization, so they inspect the traffic and they kind of spoof things so that it looks good, and then they kind of pass data over in the middle, and it looks like it's working better than it is. End-to-end encryption destroys all of that because they can no longer inspect the traffic, and you now see the real behavior of the underlying network. Watch performance go through the floor because they turned on end-to-end encryption. The only way out of it is to put the certificates on the intervening kit. That then, if you're not careful, opens you up to things like man-in-the-middle attacks, which is not necessarily what you want. So you might want to think about, has anybody been doing stuff with end-to-end encryption recently if suddenly network performance drops through the floor? Or has anybody been playing with the firewall rules? Or, other little subtleties along the way. Storage infrastructure. It's a not dissimilar story to network infrastructure. There are fundamentally two storage networks are out there. There's Fibre Channel, which is what the bigger stuff tends to use. And there's iSCSI, which is somewhat less throughput than Fibre Channel, but fairly common in virtualized environments and a lot of others. iSCSI basically uses TCP/IP networking over data network switches, so it's terribly similar and suffers the same things. You can make it work pretty well if you put in all 10 gig switches and you have a dedicated network just for iSCSI, at which point you've pretty much built the equivalent of a Fibre Channel SAN, so you might as well go down the Fibre Channel route in the first place, frankly. Fibre Channel, the switches are do cut through rather than store and forward, so the latency is lower, and you can get the I/O rates up greater than you can with iSCSI. But in a world where you've got hypervisors and lots of virtual machines and not great performance requirements, iSCSI is probably perfectly adequate for your purpose. It depends. The big thing is you now have multipath devices. So you also need operating systems and all the extra driver layers that will handle path failovers and multipath devices properly. And that tends to work better in the Fibre Channel world than it does in the iSCSI world, in my experience of the kinds of systems I'm normally working with. So that's the connectivity of the servers to the storage arrays. So that's the fabric switches make the SAN, or the iSCSI switches make the SAN, and then the storage arrays are where the actual stuff. I keep hearing people refer to, we just bought a new SAN. What they meant is we just bought a new storage array. So again, one of the problems of the computer industry is terminology. People use the same term to mean different things. And that's really confusing, especially if somebody's trying to troubleshoot it over a phone and you don't have much design documentation and they can't see it. So storage arrays, you have array controllers. The array controller hides all the disk. The disks behave in a certain way. You get given levels of performance. These days you've got things like thin provisioning and reclamation of blocks that can add to the controller overheads. You've got array-based operations like snaps and clones. Please don't leave things like snaps running for a really long time and have loads of them, because all you're doing is making the array controllers spend all their time trying to keep track of where the blocks are, not actually getting much done. Array controller performance can also be really hit by things like using RAID 5. By a long way, RAID 0+1 is the fastest and also the most expensive because you have to buy more storage. But you will really take workload out of the controllers by not using it. Because if you're doing RAID 5, they've got to be doing all the parity computations and all sorts of fun and games like that. And the stuff stays in the caches longer. Everything just behaves more slowly under those circumstances. Bandwidth to and from the array controller becomes more the limiting problem than the actual rotational latency of the underlying disks. Contention between systems for access to the storage array is important. So how many array controller ports are you presenting to face the systems? And something that's now coming onto the market, which actually is fixing some of these issues, provided you have deep enough pockets, is large storage arrays, which are all flash. So some of this data center stuff I'm doing in the States at the moment, we're looking at filling a room this size with storage arrays, and it's all flash storage. It's real quick. It's also massively expensive. But it's kind of neat stuff. The I/O latency is ridiculous. It's way, way, way down. We did some prototype tests and we bypassed lots of, it's one of those data centers where they have lots of rules that you've got to go through top of rack switching and stuff, and every switch you go through adds more latency because you're doing switch hops. Just as an experiment, we took some of that out of the way and we direct wired the machine to one of the big fast all-flash storage arrays. We got down to 0.1 of a millisecond write latency, which is stupendously quick. Real handy for catching stock exchange transactions and stuff like that. But you've got to have the money to be able to buy that kind of kit. But it's really nice. Multi-site data replication. Now this is another really interesting area. So this is an availability thing. So you're running multiple sites, you're doing all sorts of good stuff like that. What kind of performance are you going to get? Distance latency becomes really important. Yeah? So speed of light in fiber doesn't change anytime soon, and it's not going to change anytime soon. Distance latency becomes the governing factor in the latency of the system. So what we have here is that, and this is why you often have the choice of synchronous or asynchronous replication. So synchronous replication says that, right, my piece of software running on this machine here writes data to the storage here and writes data to the storage over here. I/O completion will not be returned to the software until the data is safely stashed in the array controller here and stashed in the array controller here. If that distance is only 20 or 30 kilometers, you're probably down into approaching half a millisecond at worst. Yep, so you're getting about 500 I/O writes a second. If that distance is quite a few hundred kilometers, you can be down into tens of writes a second. What does your application need? Bear in mind, reads aren't important here. Reads are not relevant because reads always come from nearest copy, so read latency is a non-issue. The issue is writes. So, if the application needs a minimum of 100 write I/Os a second, pulling the data centers apart by several hundred kilometers is a non-starter. Okay, so how do we get past that one? Because we really do need our data replicated. Well, turning on asynchronous replication says, you know what? We trust this array. Once it's got the data, it can return I/O completion status and you can carry on writing at full speed. And in the background, it'll send its data to the other array. What happens if that data center goes up in smoke or the link goes? Not all of your data is guaranteed to have made it to the other side. And most array controllers do this at block level. So this isn't file system level. So if you don't have all of the data blocks over there, you've now got inconsistent data structures on disk. Inconsistent file system. So great, you've increased the rate at which you can replicate data, but you've increased significantly the time you're going to take in order to be able to run from over here, because you have to look for and fix up inconsistent on-disk structures before you can continue. So the trade-off is the apparent improvements in performance. The downside is the risk that you're going to have to spend quite a chunk of time searching for and fixing up problems in the file system and in the file structures before it's safe to continue. Your call. And if you're doing, the best way is actually 3 sites. So you have 2 sites relatively close to each other, and then you have a 3rd site someplace else, and you might be actually pushing the data over there with async. Or maybe if it's a database, you might be using log shipping. So there are lots of different techniques for doing data replication. It doesn't just have to be the systems that do it. It doesn't just have to be the arrays that do it. Database software can do it, network file systems can do it, a whole bunch of other stuff. They all come with different mechanisms and different trade-offs, but the underlying principles governed by the latency of the link apply. So you can figure out which way is going to work best for you and how you're going to best deal with it. Hardware and operating systems. So, hardware platforms. These days we can buy some really big, serious, high-end multiprocessor systems. This thing in the States is using big HP integrity server blades. So these are things with 64 cores, each of which is about 2.5 gigahertz, 1.5 terabytes of RAM, 16 by 10 gig network interfaces, and 8 by 8 gig fiber channel interfaces. And there's a dozen of them, which is, fairly sizable kit, right? How the hell do you exploit it? How do you begin to break the software down enough to be able to run on something like that to actually be able to use the performance that you've got? And it's this interaction thing again, yeah? It's how all the software is written and how it's all interacting with each other and how you break the workloads down. We've got large server farms, massive Linux front ends, a couple of hundred Linux boxes. They're all running single instances, they're all relatively small servers, but there's a lot of them. Or you've got things like the Google search engine model where you've got vast numbers of relatively low-end servers all doing stuff in parallel. But the availability requirement from Google is very different to running a stock exchange. You can lose 2 or 3 things. Hey, the search queries will come back. Data consistency isn't quite as important. Yeah. It's not like keeping track of financial records in a banking system or keeping track of an air traffic control system. So very different requirements lead you to very different hardware choices. And as we said earlier, the current trend is towards these high core count, large memory machines. And blades, a blade server, typically you buy a chassis. In the back of the chassis are the power supplies, in the back of the chassis are the I/O modules. So it could be embedded fiber channel switches, it could be embedded network switches, it could be straight pass-throughs that take you up to top of rack switching. It depends on the data center layout. It could be virtual, what HP have a thing called Virtual Connect that allows you to do all sorts of clever stuff off the back of the servers. Fundamentally, they're modular computers. Yeah, they're not anything terribly clever, but the neat thing is that you can expand it without having to go away and replace the machine. You can just pull bits out, insert different bits. So blades bring more flexibility to the configuration and more complexity. Especially when you start doing things like firmware updates. You've now got the blades need this, the NICs need that, the onboard administrator needs that, the I/O modules in the back need this, and actually you might compromise it. If you've got too much in one chassis, you might have created yourself an environment that you can't take down to work on because all the individual bits that are running in there have got overlapping availability requirements, and you've created something that's truly 24/7, and you don't have the means of dealing with it and taking it down to make the necessary level of updates or fixes one day. So how you break everything down and allocate all the workloads to all the different machinery needs to think about the availability stuff as well as the performance stuff. So how do you deal with high core counts? Well, lots of cores on the same processor. Shared cache, that's good because we can get more throughput. Lots of multiple processor sockets bring some interesting problems that we'll come around to in a moment. Can you distribute the interrupt handling? Operating systems work by a piece of hardware delivers an interrupt. Can we offload? We don't want the primary. If we have a 64-core monster, do we want CPU 0 handling all? Dealing with all of the interrupt service? No. We want to be able to distribute the interrupt service load across multiple processor cores if we can, and that's down to operating system design. A lot of it, and some hardware design and cache synchronization and a whole bunch of other stuff. But the operating system's in charge of all of that. Then we've got, so what we're really trying to do here is minimize all the stall times. It's this, stop it going slower thing, right? And common data structures. All operating systems work by having a bunch of data structures that are core to the OS that help it keep track of stuff. Some operating systems in NUMA machines, NUMA is something I'm coming on to in a moment. NUMA is non-uniform memory access. So memory locations over here have a different memory latency when we access it from this CPU to accessing it from this CPU, because the transit time is longer. Yep. And so some operating systems will actually replicate system space so that it's in different, the same code exists in different places of the machine because it's local to where the processor is, because that way you can get more performance. Hyperthreading. General principle with hyperthreading is turn it off. Most operating system schedulers will do a better job of handling workload distribution than turning on hyperthreading. So the theory behind hyperthreading is that while a CPU, let's say it misses data in the cache and it has to go out to memory, so it has to go and do a memory fetch. While it's doing that memory fetch, which might only take a few nanoseconds, the other instruction stream can overlap and continue. So under certain circumstances, depending on the memory, on the locality of where the data structures are and where the instructions are, and the amount of local references and how much is in cache and a whole bunch of other complexities, hyperthreading can buy you a theoretical advantage under some workloads. In general, I haven't met very many of those kinds of workloads. There are some places that do some really interesting, funky stuff with maths and lots of weird things, finite element modeling, one or two bits and pieces like that. But these days, often a better technique for that kind of dedicated thing is to actually go and use a high core count GPU, graphics processor instead, because they're better designed for doing that kind of thing than a general processor, general CPU. So all I'm saying is just be aware that hyperthreading exists and think about whether you want it on or off, and the default is that the boxes usually turn up with it turned on. Most people don't know that it's there. I bought a 4-core box, it's got 8 CPUs. Yeah, well, you've got threads on. So turn hyperthreads off, you'll go back to having a 4-core box, you might just find it goes faster. Depends on your workload. But it's worth having a look. Oh, and the other thing is beware of what I call the idle loop. All operating systems have an idle loop, yep. And the idle loop is anything but idle, trust me. It's scurrying around in the background, it's doing cache invalidation, it's doing cache synchronization, it's doing all sorts of, clearing out memory regions to be full of zeros so that the next time a piece of code does a page swap in, it gets a page loaded with zeros ready to go rather than having to clear it and initialize it itself and all sorts of good stuff like that. So there's lots and lots and lots hiding inside operating systems that's really important. Non-uniform memory access is another. This is this problem where big machines, the signal transit time is such that it takes longer to get between the two, to read the data. So you can set the memory interleave behavior at firmware level. Memory physical layout becomes important. How the DIMMs are loaded into the right sockets and the right size DIMMs in order that you then get the memory, and how you lay out the data structures, and how the operating system itself starts using memory. Most operating systems have things like a file system cache, whether you know it or not. And those will burn quite a lot of memory, because that's what, memory is there to improve performance, right? So let's use it. And that's what operating systems tend to try and do. So again, it's right off into the sort of, deep into the dark innards of the OS. But if you're really trying to get performance on big systems, this is something that you have to pay attention to. Here's an example of how it works, or how a machine is laid out. So this is one of these big 64-core monsters. So it's got 8 processor sockets and 8 core processors, and you can see here that so memory attached to there. This CPU can get to the memory faster than that CPU can get to the memory over there, because it's got to go over the link. To get to here, it's got to go over another link. To get to down here, it's got to go all the way down there. And so my access times for memory vary depending on where I am in the machine. So you might want to think about biasing how the OS scheduler works, and you might want to think about how your software runs and tying it to different CPUs if you're really seriously trying to extract the maximum performance out of a system. I mean, this is not territory that too many people need to go into, right? But at least be aware that it exists. And if you're interested, look it up, because it can have some really surprising effects. Especially if this thing is actually running a hypervisor and then you've got a bunch of virtual machines running inside it and they're all being swapped randomly all over the place and different things are in different places of memory. The last thing you want is all the memory for your virtual machine over here and the CPU over here running the virtual machine, because you'll get really poor performance. So operating systems just share out and arbitrate access to the machine resources. That's really all they're doing. And they protect things from each other. They give you this illusion, this abstraction layer that it's all yours. Oh, beware of Java. Java's not actually a compiler. And it comes with its own runtime environment. It's not compiled code. So if you're after, real performance, Java's probably not the tool of choice. Languages like C++ are probably a better tool of choice. Interesting enough, another twist, if you're writing code in C, I've actually found on occasions that shoving C code through a C++ compiler will actually generate better machine code. And I can get slightly better performance under some circumstances. It depends on the compilers and the backends and the code generators and a whole bunch of other funky stuff that's going on down there. And again, this is this virtual machine thing. So as far as the machine is concerned, the hypervisor is an operating system. As far as the hypervisor is concerned, all the individual guests are workloads. And inside each virtual machine, you've actually got another copy of an operating system running, and inside that you've got a lot of other stuff running. So it's this massive hall of mirrors effect again. In general, performance tuning of an operating system has a pretty limited effect. I have occasionally managed to get some really good results, but usually because it's so badly set up in the first place. That's a fact of life. So you really need to set things up, and you shouldn't be tweaking. If you've got a system that's got a fairly predictable workload, you probably don't need to be tweaking it very often, kind of set it up. You need data. You need to review the performance behavior over time, but on the whole, it's pretty static. But most wins are to be had here, down and looking at the code. Writing better software. Stripping out all the stuff you don't have to do. Or rearranging the order in which the workload happens. If you've got a system that needs to scale up really big, many tens of thousands of instances, some big web server thing, for example, you might find that a trade-off of loading a load of things in memory at the beginning and getting everything ready, which might take you longer to get started, but then running a really tight amount of code for every instance, gives you a far better result than every instance doing an awful lot of loading of information and checking. It might be great, it might scale up really nicely to 50 or 100 instances, but if you're scaling up to 10,000, 50,000 instances, 50,000 doing an awful lot of stuff you don't need to do every time adds up to a hell of a lot of wasted horsepower. So this is the virtualization thing. I kind of like this quote. This comes out of there. Basically, virtual equals not physical, but you all know this anyway by now. So this is no more than a diagram that explains what we've really just been talking about. There's some big servers, there's the hypervisors, there's the virtual machines, there's an operating system. Finally, we have some applications. These talk out through a storage path. They get to the storage array. They finally talk to some data that lurks on what this thing thinks is a disk. This thing, of course, thinks it's an operating system running in a computer. Actually, it's running in It's this, or the other way of looking at it is these Russian Matryoshka dolls where you sort of pull them apart. That's another way of looking at it. And the same with the networks. So that's really what's going on. So if you're trying to performance investigate something in here, you actually need to know about all of the rest of it as well. Because your problem probably isn't here. It's probably someplace else. And what level of interactions have you got? What's going on? How does it all hang together? It's this holistic view of the world. Cloud. There's an interesting twist. Public cloud services. Yeah, latency is going to happen. You're not going to get great latency if your data is on the far side of the Atlantic. Does that matter? Depends what you're doing. Yeah, it might matter a lot. So, I mean, cloud, don't get me wrong, you know, cloud has got some really good things going for it. You know, the ability to spin up instances of machines without having to think about it, kind of, you know, the pay-per-use model, you know, software as a service, all of those things are great. But depending on how it's implemented, it could be really quite successful or it could be really quite disastrous. You know, you might find that actually having your own, you know, building your own cloud services running out of your own data center, where all of the network layers and everything else are under your control, gives you a much better result than stuff that's running somewhere that you don't really know where it is. So it does, and fundamentally, it's unsuited for things like high I/O write rate systems. If you've got a system that needs 1,000 write IOs a second, you're probably not going to get that out of any cloud platform, be it public or private. So you can actually, from a design point of view, make some fairly rapid decisions about the suitability of some of these things by understanding the behavior of your applications. And if you need things with low and consistent latency, it's probably pretty darned unsuitable as well. You know, your mileage may vary somewhat, as they say, but as a general set of guidelines, yeah, that's a fairly usable starting point. So, design, performance, testing, understanding the whole thing. It's all the same stuff, right? You know, so what are we trying to do? We're trying to size systems that can handle big pikes. Yeah, it's the concert hall foyer problem again, right? Taking out the wait states, working on the code, stopping it do stuff. Anybody here use EasyJet, speedy boarding? I call it speedy queuing. You just get to queue more quickly, right? That's the thing right there. Faster machine just waits more quickly. So all of these are sort of, you know, nice little sort of jokey things to say, but actually behind them, there's some useful meaning. So how does your code behave? How do you do it? The real thing is down here. Thinking parallel, not sequential. Have a good journey back, Jamie. So understanding all of that stuff is really, really, really key. And writing code that scales up. This is the uniprocessor, multiprocessor thing with the inherent parallelism stuff I talked about earlier. Lots of old code out there, right? Lots of old code didn't use operating system mechanisms very much. You know, people tended to bung data in memory, use their own flag bits, a whole bunch of things like that. Those are just the kind of things, if you're porting that code to a new platform, that will bite you, now or later. Your testing has to find that out, and the sooner you find it out, the better, because it'll hurt less. Finding out some of this stuff in production is a very bad place to find it out. Compilers. Understand, you know, have an understanding of what compilers do. You don't have to, you know, go and look at the results, unless you're really, you know, kind of pushing the edges. But understanding what they do. You know, they generate the IND streams, yeah, and they push it into different parts of memory, and then it gets, you know, loaded, turned into an executable image, and it gets loaded into memory, and yeah, then it generates things like ELF and dwarf formats for debugging and a whole bunch of other good stuff. And it generates the code for the target machine architectures. And the optimizations in compilers will often do some reordering to take advantage of underlying instruction sets. And you'll often find that there are switches on compilers that will let you take advantages of instruction sets for more recent microprocessors. So you might choose to target only a certain generation of processor and later, because it's got certain instructions in there, and if the compiler takes advantage of those instructions, actually you can get a better performance. Because otherwise the compiler is going to generate code that will run on every machine, and that might not be appropriate for what you're trying to do. So, limits to performance. Can you make use of all this hardware parallelism? Can you actually make use of the machinery at your disposal? And a lot of that comes down to designing the data layout, the granularity of the data structures, and the synchronization techniques you can then take advantage of or not. Fundamentally, that's your problem. Designing and writing really good code needs really good programmers. And there's a massive difference between the really good ones and the rest. The really top people are really that good. You know, the guys writing operating systems and designing, you know, how do you target an operating system to run efficiently on a specific hardware platform, have got a really good understanding of how a lot of this stuff behaves. And also a lot of these people will actually, you know, they publish stuff on YouTube, lots of other places. And these are things that are worth understanding and listening to and finding out more about. Because that is a skill that's really in scarce supply. This is another interesting, this is why virtualization can work, by the way. So, you know, we're looking at I/O rates of, oh, we might be down into a few, you know, oh, 0.1 of a millisecond, that's really good, yeah? 0.1 of a millisecond is actually a really long time in the context of a CPU running at 2 gigahertz, yeah? Because the instruction cycle time is about half a nanosecond, yeah? So we can get, ooh, 4,000 or 5,000 instructions, you know, lots of instructions executed for just the time, or millions of instructions in cases, executed in the time it takes to send data to disk, right? That's how virtualization can work. Because we can burn CPU cycles to create the illusion of an I/O device inside the hypervisor. And if we're in charge of the device drivers on both sides of the wall, we can actually do better. And we can do what's called para-virtualization and, you know, have the virtual machine talk directly to the hardware. And so there's some really interesting differences here in performance. And so we can actually get a lot of instructions executed in the time it takes to do a very small amount of I/O. But then we need lots of tools to help us debug all this stuff and understand it. So we can capture information, measure information, take performance data out of all sorts of stuff. And the really interesting thing is it's all got to be time synchronized, and if it's nicely synchronized in time, we can actually start to line things up, and we can see things that might be relevant, that might cross-correlate and give us a clue as to where the performance bottlenecks are, and go looking at the different things that are happening. Yeah. And you know, this is Heisenberg's principle, yep. You know, the act of measurement affects the measurement. So build the instrumentation into the code. Don't add it when you need it and take it away afterwards, because if you leave it there all the time, you'll get more predictable behavior and you'll have built-in logging when needed. And pay real attention to this state transition event timing stuff. It's the wait states and the cache synchronize. It's all these stalls that are really expensive in terms of performance. So this is all again about making it, you know, stopping it going slower, stop it waiting. Think about how you can get things parallel. Think about what actually needs to synchronize with what in order to be able to proceed. The big thing is this, you know, testing for scale, not just functionality. Find out what really happens. And if something bad happens, how on earth do you find out what happened? You've got to have information and data to work from, especially with transient problems. And you need it fine-grained enough in time to be able to see the problem. You know, there's no point in running a 1 second sample rate for something that's over and done in 1/10 of a second, because you'll never see it. So you might need to go digging inside the operating system, inside, you know, system analyzer. You might even need to go, you know, modern microprocessors have actually got, you know, some of the Intel stuff has got actually built-in things that you can turn on that will do instruction tracing, all sorts of fun stuff deep down in the internals that can be really useful to look at. So I'm afraid I come back to the, you know, it's important to understand the whole thing. And you've got to have data to look at it and look at trend analysis over time. I kind of like the, you know, it's slow, what do we do next? Well, okay, so without data, you know, we're just guessing. You know, my guess is as good as anybody else's. You know, I can walk up to a system, you know, yeah, well, what's wrong? I have no idea. I need information to be able to look at it. And don't jump to conclusions. This is another big danger. Just because something correlates doesn't mean that there's actually a cause and effect going on. It might just be, sheer coincidence. And most evil problems are combinations of lots of things all happening at the same time, or arriving at a similar enough time that they affect each other and then cause you a lot of trouble. And if people say something's slow, what are they, this is really interesting, oh, it's slow, it's running slow. Okay, so, right, so we've just migrated to a new platform, it's running really slowly. Okay, is this actually a problem that's been there for forever and that they're just using the excuse that something's changed to complain about it again? That happens a lot. You've seen this, haven't you? Yeah? So, is it genuinely responding poorly? Okay, what's going on? And where is it? So you've got this big complex system, this network talking to this, talking to this, talking to this, talking to this. Build instrumentation through the system. If it's a web server, okay, so we're providing data over the web. Right, so the customer's somewhere else is experiencing, they say, terrible performance problems. Right, so in my office, I'll use an ADSL internet connection, just like they might be, and I go out to the internet and I come back. Do I get terrible performance? Yes, great. That means that they're reporting a real problem. Okay, now let's move closer to the systems. So put another test point just outside the firewall connecting to my company. Do I get terrible performance? No, great. So the problem is between there and there. Luckily, that's the internet provider. That's got nothing to do with me. Fantastic. Thank you. Yep. And I can save so much time by knowing where the problem is. Or it might be that actually, yes, I've got terrible performance on the outside of the firewall, and I've got good performance on the inside of the firewall. Okay, well, that gives me a real good clue. And so on and so on and so on. So just build test points in where you can actually do real monitoring that gives you real information that lets you hone in on where the trouble is. And it ain't difficult to do. And fundamentally, the question you always have to answer is there actually anything wrong? Is this expected behavior? Because it might just be that the answer to that is, it's all fine. Or it might be that somebody, it depends who it is as well, right? It might just be that somebody says, I don't really look at this. And and because this person is really good at reporting, interesting and unusual circumstances, somebody might just have noticed something that's about to bite you. So paying attention and going looking and having all the monitoring in place could just make you go, that's interesting. I didn't realize we'd lost that network link. Oops, because the monitoring didn't pick it up and the alerting didn't happen. And so nobody knew about it. But we've now got the whole thing primed to go horribly wrong fairly soon, and we can catch it and fix it before too many people notice, which is a good thing. So one of the other things that's going on here is I find as a useful design technique is, can you segment a system? Can you sort of protect it against catastrophic failure? This bit's gone bang. Right, okay, can we constrain the failure and stop it propagating further and taking things out? Even if things go horribly wrong, can we make sure we don't lose or corrupt data? Because it's bad enough having a system go down, but if the data's toast, then it just gets really difficult. We have to go back and restore from backups. Anybody remember the BA catastrophe? Was it a couple of years ago? Was it last year where they lost a whole bunch of flight records and people were sort of queuing at airports and waiting for days because they couldn't get stuff done? So that's a good example of something like that. Or was it RBS? A few years ago managed to lose a whole bunch of stuff and take their systems down and nobody could get money out of holes in the walls or find out what's going on. Or recently we had the TSB thing. Yeah, these things keep happening. And there's usually a collection of reasons like this underneath it. And understanding that it's the recovery from failure that has the biggest thing. So testing under all circumstances becomes really important. So, some typical problems. That's probably the biggie at the top, really. Too many people interested in cost, not enough people actually understanding how it works. And then making poor decisions as a result. If you deliberately make a decision to go low cost, that's great. But if you unknowingly make the decision to go low cost because that's your default position, that's not so great. Because it might just come back and get you. Most systems, in my experience, tend to be I/O write rate limited in some way, in some shape or form. Often it's inappropriate use of virtualization. I've lost track of the number of times I've had people say, our SQL server's going really badly. And my standard first question now, okay, so have you virtualized it recently? Oh yes, well, maybe you want to think about whether that was a good idea or not. Try going back to oh look, now we've unvirtualized it, performance is much better. Okay. How many other machines is it sharing it with? Think what you've done with the I/O, because when you virtualize something, you kill the I/O write rates to disk, unless you do para-virtualization and a whole bunch of other stuff. So, just needing to think. Or systems that don't scale well. Or insufficient granularity in your data. All of these things are what show up because of the underlying principles around scalability, parallelism, wait states, and all the things that an operating system designer would pay attention to. So, I don't think performance can be, it can't be bolted on later, nor can availability or security very easily. Think parallel, not sequential. That's one of the real big messages. Testing's got to be realistic enough. And it comes back to this holistic view of the whole thing. And, ultimately, you generally get what you pay for. Two corners, choose them, it won't be the third. Guaranteed. So, thank you very much. I hope you found that interesting and useful. I've certainly enjoyed doing it, and it's been quite a lot of fun, really. So, thank you all. What do you want to do next? Do you want questions and stuff? Or?
We've got questions. If anyone's got any questions, we've got another 4 minutes or so. So might be holding people up that go on the fringe now.
True.
Well, the slides available?
Yeah.
Yes. The full stream of tonight's session will be available if you just go to the www.edinburgh.bcs.org. You'll find all the information there, and that's all the slides.
Yeah, the slides will also be up on my XDelta website at some point in the next day or so as well. There's a previous version of them. I gave a similar talk in Leipzig earlier this year, so there's a pretty similar slide set up there already from that. Shoot.
One of your slides that showed the abstraction layers with the applications at the same time, and what I've kind of taken from that and other things you said, problem solving, is that you're actually probably better looking from the inside out the way to find the problems, start with the application. Is that a fair assumption?
Yeah, but trace the whole thing through. So if I'm problem solving, okay, so here's how I attack a problem. So I look at what they're trying to do. I try to understand what they were attempting to achieve. I pretty rapidly work out roughly how I'd go about solving the same thing. And I then look at what's in front of me. Where there's a reasonable match between what I observe and how I would think I would do it, I move on. Where there's a big mismatch between how I think I would do it and what I observe in front of me, I make some notes. And that way I can rapidly pick out the high spots and go back and looking. And what you then do is start drilling into it, and you start going, okay, so this is this layer. We start at the application layer. What's the behavior we observe? How are things behaving? What's really going on? Okay, so what could be affecting that? Right, so the environment it's running in is here. Okay, so it's a hypervisor. So what else is going on within the machine at the same time?
That's really the point I'm trying to make, is that
digging in.
a point to start at.
Yes.
I'm not suggesting for a moment that we don't look at all the layers, but from a bit of work on this again, as you start, you're starting to say, in terms of that abstraction,
Yes, absolutely.
application, and then try to understand what's happening here, and then dig deeper down those layers.
Yeah, but also this monitoring through the infrastructure can be really helpful as well, because that can give you another starting point. So actually you're looking, you're almost looking for multiple starting points to attack the problem.
There's a bit of a trick to that one, is you have to have people who are expert in all these different areas to properly problem manage. That's my experience anyway. Most of us are, as you described at the beginning, we're all kind of siloed. We've got all these different areas of expertise who don't actually communicate all the time.
And that, I think, is something the industry needs to work on fixing. And I think most organisations need to work on fixing, and actually having people who have got a reasonable understanding of most of it. And those are the people who are really invaluable to you when things start going bad. That's what I'd like to see happen. But yeah, I tend to start by, what are they? What's the reports, and then drilling in. Sorry, if you would like to.
Yeah, that's the challenge. You need to be a database expert, network expert, and everything put together, then you become a performance engineer. So to reach there, I think whether you retire things, that's how it's very difficult to manage everything as a whole.
It is.
Yeah.
Yeah, but there's an awful lot of knowledge and experience that you need in order to go looking. And also, the more you do, the easier it gets.
True.
I think. The downside of that, if you have a lot of experience, is you end up with too many preconceived ideas, and you can waste an awful lot of your time chasing what you think is a problem, and actually you're going in completely the wrong direction, and you're making a load of stupid assumptions because you're going in with too many preconceived ideas. And that's why I said what I said about trying to throw away the preconceptions and just look and be observant and listen. It's really hard. It's really useful.
Any other questions? Thank you very much for coming along, Colin.
That's all right. No, I enjoyed doing it. It's been kind of fun.